Section 4.3, Maxima and Minima. We have a definition here of minimum and maximum. So, suppose a function is defined over a certain interval. If there is a value in that interval, in this case we're calling it c, such that the value at c is greater than the value of any other x value, every other input in that interval, then it is called an absolute maximum. It is the highest point or the largest y value on that interval. Similarly, if that value at c is less than every other value on that interval, then we call it an absolute minimum. It is the absolute lowest or smallest y value on that interval. In either case, we refer to these as absolute extrema. They are the extreme values that the function takes on, y values it takes on in that interval. You can also call them global extrema. Meaning it is on the entire domain. So again, our maximum or minimum y value, it's our y value, that is our extrema. Okay? We can definitely say when they occur, so we'll try to say that as we go through here. So determine the absolute extrema of each of the following functions by graphing. Now some of these are not given a domain, so we assume that it is whatever values we can apply the natural domain. So example 1, f of x equals x cubed. All right, well, if I'm looking for a highest or a lowest value, the highest value, the absolute max, well, there isn't one. There is no highest value for that function. Okay, well, same thing for an absolute minimum. We don't have a lowest value. Okay, bad example. Let's try this next one. F of x equals 1 over x squared plus 1. Well, there is a highest value, a maximum, right here. So we have got an absolute maximum at x equals 0. In fact, let's say this. An absolute maximum of 1 at x equals 0. So the maximum point is 0, 1. All right, now for a minimum, an absolute minimum, there isn't one. There's not a lowest point. It gets closer and closer to the x-axis. All right, cosine x. Well, there is a highest point. The highest point of this function is here, and here, and here, and here. There are lots of places. So our absolute max of 1 at x equals, and it happens at all multiples of 2 pi. So at pi, or at 0 pi, 2 pi, 4 pi, 6 pi, positive and negative. So the way that this is usually written is we're going to say plus or minus 2k pi. So every other, in fact, we can write that differently as at x equals, let's see, we've got 0 plus or minus 2 pi plus or minus 4 pi plus or minus 6 pi, etc. So it happens at every value that's an even multiple of pi. Now our minimum values are these alternating. Well, these are the values of the odd multiples of pi. So the absolute minimum of -1 occurs at x equals plus or minus pi, plus or minus 3 pi, plus or minus 5 pi, etc. So at the odd multiples of pi. All right, number 4. We have this function on the interval from 0 to 4, and it's a piecewise function. Absolute maximum occurs at this point right here. So an absolute maximum of 2 at x equals 0. and we have an absolute minimum. We don't actually. There's not a lowest value. Okay, so we do have none there. All right, example 5, x minus 2 quantity squared. Again, this is on a closed interval. So an absolute maximum of 4 at x equals 4. All right, and then we have an absolute minimum of x equals 1, no, av 0. Oh, hold on. Say that differently. Absolute minimum of 0 at x equals 2. All right, and our last one of these, absolute maximum. Well, there is not one. However, there is an absolute max of 0 at x equals 0. Oh, I meant to mark these up on this last one. There's our maximum. There's our minimum value. Here we have our minimum value at 0. Okay. A theorem we have is the extreme value theorem. This has to do with finding extrema. If f is a continuous function over the closed bounded interval a to b, then there is a point in that interval a to b at which f has an absolute maximum, and there's a point in that interval where f has an absolute minimum. So we want to pay particular attention to the hypotheses here. F must be continuous over a closed bounded interval. So let's go back and re-examine each of these. All right, well, number 1 is a continuous function, but it's not over a closed bounded interval. So we're not guaranteed to find a minimum or a maximum there. Okay? Example 2, that is a continuous function. It's not on a closed bounded interval, but there is a point that is a maximum. Now, we are, however, not guaranteed. So what that theorem says is, if these things hold, if each of these things hold, then there is a point. It's not saying there won't be if there isn't. If those conditions are not satisfied, that doesn't mean that it won't have a maximum or minimum. It just means we can't guarantee that there is one. All right. Well, number 3 is continuous, but not over a closed bounded interval. And again, we do see that there are minimums and maximums, but we can't guarantee that. Number 4, that is not a continuous function, so we can't guarantee minimums and maximums, but there happens to be one there. Right. Number 5, this is a continuous function over a closed interval, 1 to 4, closed and bounded interval, and there is, therefore, we can guarantee a maximum and a minimum, so we see that those both exist there. And then number 6, that function is continuous, but not on a closed interval. That is half open. So we can't guarantee there's going to be a maximum, minimum, and a minimum. There is, however, a minimum, as we noticed there. All right, so you might think about that. All right. Next, up to this point, we have discussed absolute and global extrema, or global extrema. Now we turn our attention to local extrema. So the basic idea is that rather than having over the entire domain a highest or a lowest value, a y value that is, in a certain interval, if we have a value c such that the f of c, the value there, is greater than or equal to f of x for all x in that interval. So in a particular region of our graph, if we have a highest point in that region, then we call that a local maximum. Similarly, if we have a point c such that the y value of c is less than or equal to f of x for all x in that interval, in that region, if it is the smallest, it's less than everything in the area, then that is a local minimum. All right, now we next say we define what a critical point is. So a point C is a critical point of f if f prime of c equals 0. or f prime of c is undefined. Now, there is a theorem called Fermat's theorem that says if we have a minimum or a maximum on an interval, it is going to occur at a critical point or an endpoint if we have a closed interval. So critical points or our endpoints are the values we could check out for a local or absolute extrema. So let's go ahead and look at this function. So we'll want to set the derivative equal to 0 or see where it is undefined, and endpoints. So if I take the derivative of that function, that will be just x squared minus 5x plus 4. Okay, now setting that derivative equal to 0, well, it's a quadratic that we can factor. X minus 1, x minus 4, which means we have x equals 1 and 4. So we have two critical points of 1 and 4. Now we're not getting a closed interval here, so those are the only values we need to check. So let's go ahead and make a chart, x, f of x. So the value of f at 1. So I'm going to plug that back into the original function. Alright, so 1/3 times 1 cubed minus 5/2 times 1 squared plus 4 times 1 is 11/16, or 11/6. Right, now if we evaluate that function at 4, 1/3 x cubed minus 5/2 x squared plus 4x. Alright. That is -8/3. So we have a local maximum of 11/6 at x equals 1 and a local minimum of -8/3 at x equals 4. Now, if we sketch this graph, our graph looks something like this. It's a cubic. So we definitely will have a maximum and a minimum. So that graph verifies what we just see there. All right, number 8, f prime of x. The derivative of that would be 3x squared minus 1 with our chain rule of squared times 2x. Now, setting that equal to 0, we can see that we're going to have x equals plus or minus 1 from that term there, and x equals 0. So we have 3 critical points. The derivative is never undefined. All right, so let's go ahead and plug these values into a table. So x, f of x. So we're plugging these into the original function. All right, we'll evaluate this at -1, 0, and 1. So at -1, we have a value of 0. At 0, we have a value of -1. And at 1, we have a value of 0. Okay. All right, so we know we have a local maximum of 0 at x equals -1 and 1. Okay. Now, that may seem strange because we have 2 values there. So this may depend on what our function looks like. because if it increases past those 2 points, because like the last one we had a cubic, so it appeared to be lower on one side than the other. Okay, so let's go ahead and continue writing this. So a local minimum of -1 at x equals 0. All right, now what this function looks like is something like this, which I knew in advance. Okay, so I've obviously got a minimum at 0. That was this right here. So this actually is an absolute minimum. It's actually an absolute minimum. However, these 2 points at -1 and 1, neither one of those are actually a maximum. They are critical points, however. So that is worth noting. That's why we want to check these with our graph. Now we are going to see something called the first derivative and the second derivative test in a couple of sections that will help us do this a little more precisely. All right, number 9, we will find f prime of x. So this will be low d high. So 1 plus x squared times 4 minus high d low over low low 1 plus x squared squared. All right, which will simplify to -4x squared plus 4 over 1 plus x squared squared. So we want to look for where the derivative is 0. And the derivative is 0 whenever the numerator is 0. So -4x squared plus 4, which means x equals plus or minus 1. And the denominator will never be 0 because we have 1 plus x squared. So we never have f prime of c being undefined. But we have critical points at -1 and 1. So let's plug those values in. All right, so 4x divided by, into the original function, 1 plus x squared. Okay. So plugging in -1, we get a value of -2. And plugging in a value of +1, we get a value of +2. So at first glance, we have a local max of 2 at x equals 1, and a local minimum of -2 at x equals -1. Right, now looking at the graph of this function, a sketch of this, we have something that looks like this. So at the ends, positive and minus infinity, it's approaching 0. So we have a minimum here and a maximum here. And in fact, these are absolute min and max. And there we have it. Alright, next we have this one over a closed bounded interval from 1 to 3, so our endpoints will be valuable to us because, as we said previously, wherever we have a critical point, that is where f prime is 0 or f prime is undefined, as well as our endpoints. So if we have endpoints, we want to check those. Alright, so f prime of x equals -2x plus 3. So setting that equal to 0, it'll never be undefined, but setting it equal to 0, we get x equals 3 over 2. So we want to evaluate each of these. All right, -x squared plus 3x minus 2. All right, so evaluating at the point 1, 3 over 2, and 3 are endpoints. So evaluating at 1, we have a value of 0. 3 over 2, we have 1/4. And at 3, we have a value of -2. So it appears we have a local local max of 0 at x equals 1, or these are our potentials, I should say. Local max of 1/4 at x equals 3 over 2, and a local minimum of -2 at x equals 3. Alright, so our graph, since we do know what the endpoints look like, at a value of 1 it is 0. This is quadratic, so at 3 over 2 we have a positive value there where the slope is 0, and at the value of 3 we have -2. So we have a graph that looks like this. All right, so it looks like we have an absolute maximum for that second one. Absolute maximum there at 3 over 2. An absolute minimum at x equals 3. And the first one was in fact local. All right, now for our last equation, we will find f prime of x equals 2x minus 2x to the -1/3, which is 2x minus 2 over x to the 1/3. Now, let's go ahead and make a common denominator. 2x to the 4/3 minus 2 over x to the 1/3. Now, setting that equal to 0, a little bit of algebra tells us we have values at plus or minus 1, where it's going to be 0, and it's going to be undefined. The slope is at x equals 0. So let's go ahead and evaluate each of those. Okay, good. All right, if we evaluate that at -1, -1 is actually outside of our interval, so we don't need to test that value. So we've got our endpoints of 0 and 2, and then we have the critical point of 1 that we need to work with. So at 0, the function is 0. At x equals 1, the function is -2. And x equals 2, we get -0.762. And it continues. Alright, so it appears that we have a local, let's go ahead and call it a max until we see otherwise, maximum of 0 at x equals 0, a local minimum of -2 at x equals 1, and a local minimum of -0.762 at x equals 2. All right, now that graph, again, based on those endpoints, we can say it is at 0, 0, 1 it is -2, and then at the endpoint 2 it is somewhere here. So it looks something like that function. So we can verify that we have an absolute max at x equals 0, a local max, so it actually looks like at x equals 2, this is a local maximum. Okay, and we have an absolute minimum at 1. Okay, so remember, we want to set the function, the derivative equal to 0 to find our critical points, and that's where it's 0 or undefined, and of course our endpoints. All right, that brings us to the end of this section.